Sir, I am there, audible.
Yeah.
Is it live?
No, yes.
Yes, ma'am, it's live. It's live.
Dr. Naveed.
Okay. Namaskar. I hope you all are safe and in good health in this pandemic time. I'm Dr. Naveed Kaur, currently working as a scientist in the Bridge Engineering and Structures Division of CSIR CRRI. Respected Director, CSIR CRRI Professor Satish Chandra. Our chief guest, Shri V.N. Hegde, CEO of Stoop Consultants Mumbai. Srimati Debjani Raychaudhuri, daughter of late uh, Dr. P. Raychaudhuri, Head BS Division, Dr. Rajiv Goel, my dear colleagues from CSIR, CRRI, and finally the huge gathering of intellectuals and participants from all over the country. I extend a very warm welcome to all of you to the Dr. P. Raychaudhuri Memorial Lecture. This lecture is the third in its series, which is being organized online this time by CSIR CRRI. This lecture series is organized to honor the professional contributions of Dr. P. Raychaudhuri to the nation. Now, we are glad to share that we have got an overwhelming response for this lecture this time with almost 1100 registrations from all over the country. As a protocol of this online event, I request all the delegates to kindly keep their mic on in mute condition unless they are speaking. The participants can type their questions or suggestions in the chat box or maybe in the question answer box, which we will try to take up during the lecture or maybe during the discussion session where they can also raise their hands to ask their queries. That will happen after the lecture. Now today we have Shri V.N. Hegde, who is the CEO of Stoop Consultants at Mumbai, as the chief guest of this event. We thank you, sir, for accepting our invitation and taking out time for gracing this event with your presence. I request the CCN team to help in giving him a virtual bouquet as a token of warm welcome extended by CSIR CRRI. Thank you. Thank you so much. Now moving ahead, I welcome Srimati Debjani Raychaudhuri, who is the daughter of late Dr. P. Raychaudhuri. Thank you, ma'am, for continuing your father's legacy of service to the nation by supporting this lecture series, which is enabling knowledge dissemination at this esteemed and a large platform. This lecture series has created a tremendous pool of knowledge, which has not only become a lightning guide for the scientific fraternity, but also acted as a source of inspiration for the future generations. I again request the CCN team to help us in welcoming Srimati Debjani Raychaudhuri with a virtual bouquet for all her efforts and contributions toward this lecture series. Thank you so much. Thank you so much. Now I invite Dr. Rajiv Goel, Head of Bridge Engineering and Structures Division, CSIR CRRI, who is the backbone of this event, for his welcome address.
Thank Dr. Naveed. My own behalf and on behalf of CRI, welcome our Director, Professor Satish Chandra, Engineer V.N. Hegde, Chief Executive Officer, Stoop Consultant Mumbai, who is going to deliver special lecture today on very important topic, lesson to be learned from bridge failures. Dr. Minati Raychaudhuri, wife of late Dr. Raychaudhuri, Mrs. Malini, a doctor settled in the UK, and Mrs. Debjani, architect in Gurgaon, daughters of late Dr. P. Raychaudhuri, other members of his family and colleagues and his friends, Dr. P. Lakshmi, Chief Scientist CRI, participants from across and abroad, and my fellow colleagues from CRI. CRI was established in 1952 and is a laboratory of CSIR. In CRI, there are 7 R&D divisions, including Bridge Engineering Structure Division. The emphasis of Bridge Division is to carry out work in the following areas. Some of them are analysis and design of bridges and other civil engineering structures, application of advanced composites for bridge construction rehabilitations, distress diagnostics and rehabilitation of bridges and other civil engineering structures, bridge maintenance management systems, structural health monitoring of bridges with instrumentation, health assessment and rating of bridges, evaluation of load carrying capacity of bridges, formulation of codes and guidelines, use of waste materials such as fly ash, CND waste, etc. in the concrete, application of piezo sensors for health assessment, development of drone for inspection of bridges, development of robot for underwater inspection of bridges, characterization of various loads for bridge design, corrosion studies in bridge and other civil engineering structures, fatigue studies on bridge components, wind tunnel studies, liability characterization for bridge design and evaluation, vibration studies of structures, bridge aerodynamics, development of software for structural applications, quality assurance during bridge construction, etc. We have the state-of-the-art facilities in our division, such as structure testing laboratory, dynamic cum heavy testing laboratory with fatigue testing system, wind tunnel facilities, mobile bridge inspection unit for inspection of bridges, field instrumentation facilities, non-destructive facility for concrete and steel, biaxial test facility for neoprene bearings, test facility for bridge equipment joint is going to operation shortly. I will give you some background about this lecture. Sometimes in March-April 2018, family of Dr. P. Raychaudhuri approached CRI with a request to start this annual lecture series in his memory. Our director, Professor Chandra, was kind enough to accept their request. First such lecture in this series was organized on 29th August 2018, in which Professor Mahesh Tandon, Managing Director, TCPL, gave the talk. Second lecture was given by Professor Tarun Kant, who is Emeritus Professor and INSA Senior Scientist, IIT Bombay, on 28th August 2019. Now I will share some memories of Dr. P. Raychaudhuri. Yeah, you see that these are photographs of Dr. Raychaudhuri when he was younger days and at the time of his retirement. These are the glimpses of some of the projects in which he was involved: Howrah Bridge, Kolkata; Tusk Bridge, Northeast; Chaudhary Bridge, Goa; bridge inspection being done by his and his team; bridge testing laboratory in CRI; structure floor laboratory in CRI, which is still being used nowadays, as using these facilities. And these are photos, these were his team. With this background, I will now briefly introduce Dr. Raychaudhuri. He was born in Bogra, which is presently in Bangladesh, on June 20, 1932. He completed his schooling in Calcutta and obtained BSc Honours Physics in 1951. He did BTech Civil Engineering in 1955 and MTech in Structural Engineering in 1956 from IIT Kharagpur. He joined CRI in 1957 as a Senior Scientific Officer in Concrete Division. He received the prestigious Commonwealth Scholarship and completed his PhD from University of Leeds, UK in 1964. After completing his PhD, he joined the newly created Bridge Division at CRI, which was then under the additional charge of Sri T.K. Natarajan of Soil Division. Dr. Chaudhary was the first full-fledged head of this division who developed the state-of-the-art infrastructure in the division with dedication and innovation and with the assistance of optimal staff, and made it a center of excellence in the areas of condition survey, testing and rehabilitation of bridges. His other areas of research interest include bearings, equipment joints, well foundation, retaining walls, rigid pavement, space frames, etc. He was given the additional charge of CRI workshop and CRI Maharani Bagh staff quarters and the area coordinator for rigid pavement, bridge and instrumentation division from 1986 to 1988. He rose to position of Scientist F before taking VRS in 1988. Out of his 31 years of service in CRI, He worked for 24 hours in Bridge Division as its head. After taking VRS from CRI, he was associated with several reputed firms as a structural consultant advisor on various projects of national interest till his demise on 24th August 2016. Some of his major contributions in CRI as follows: design and construction of test bed for strong test floor laboratory, commissioning of biaxial loading machine for testing of bridge bearings, development and utilization of suspension bar method technique for deflection measurement, which we are using it, development and utilization of long length gauges for strain measurements, development and utilization of underside pulling technique for load testing of bridges, large mobile test bed for PED division in CRI, commissioning of UTM for PED division CRI. Some of the externally funded projects in which he has worked are condition survey of Vivekanand Setu, Calcutta, old ITO bridge, New Delhi, first Thane Creek bridge, Mumbai, Ramajan bridge, Kishanganj, Bihar, condition survey and load testing of Arkish bridge near Jawahar Tunnel in Jammu, Safdarjung flyover, New Delhi, Howrah bridge, Calcutta, Tejpur bridge over Brahmaputra river, Assam. Structural consultancy for proof checking and execution of Indira Gandhi Indoor Stadium, New Delhi. Condition survey of expense joints of Multan flyover in New Delhi. He was fellow of the many professional bodies, including Institute of Engineers, India. He was also associated with several technical committees of Indian Road Congress and contributed towards preparation of a number of codes and guidelines. He was called Motuda by his classmates as he was 75 kg in weight. He was very good in dramatics. He was fond of outdoor games such as football, cricket, hockey, etc. He also liked indoor games like carom and quizzes. I would like to once again, thank you very much. Jai Hind.
Thank you, sir. Thank you, sir, for giving a brief about the bridge division, about this lecture series, and introducing the gathering with the contributions made by Dr. P. Raychaudhuri. Now I request Shri Debjani Raychaudhuri for enlightening us with some insights about her father, late Dr. P. Raychaudhuri. I'm sure that will be acting as a source of inspiration for all of us.
I will like to thank the director, CRRI, and head of Bridges Division for permitting and organizing the third memorial lecture series in the name of my father, Dr. Prabir Raychaudhuri, even under these unprecedented circumstances, and I'm overwhelmed by the response it has seen online. We as a family think this is a great privilege, a series in CRRI in the memory of a scientist who worked here. I've been asked to speak about my father, who I'm sure is here in spirit. While participating in the trial run for the event, I thought what my father experienced here firsthand, that there was a sincere effort by all concerned for a shared goal. I'll really like to thank all the team involved here who made this a reality, and because this was online event, so a lot of effort was put in for this. So thank you very much. Even though he retired in 1988 from CRRI, he had close bonds with all his colleagues, his juniors, the library and the canteen. He made it a point to attend all Science Day functions at CRRI. He always thought of this as his family home. My father was remarkable in his understanding of complex problems and simplifying them. Let me share an incident from his early life. My mother was pursuing her PhD at IARI in the early 70s. One day she was very distressed in the morning as she had missed preparing for an important test. While she was getting ready, he quickly read up a couple of chapters on plant virology and explained to her the significant points on the drive from our home at Lajpat Nagar to Pusa. My mother passed the test with flying colors. Her professors would later joke that he deserved half a PhD because he had the ability to check, to read, and to assimilate anything, whatever he read or heard. That was his remarkable quality. My father was also gifted with great intellectual tenacity and believed in the systematic application of the first principles to all complex problems. And that is why, after his voluntary retirement, he was actively associated with several leading bridge consulting organizations as a consultant, especially on bridge repair work. In fact, he was also associated with Stoop, and I'm delighted, and our family also, that the lecture today is being presented by its CEO, Shri V.N. Hegde, and the topic chosen is something very close to his heart, bridge failures, because this is something you learn the maximum from in this line. That was something he would say. He would say anybody can create a new bridge, but to learn what is from the defect to repair something is the art of understanding and then applying. He continued working as a consultant at the very end of his life. Even in his later years, when his eyesight started failing him, he had a person who would read to him all the important documents and test results, and was all explained to him orally, but he was able to grab them, summarize productively, and give his advice on them effectively. We spent some remarkable years in the CRRI residential campus. There he enthusiastically conducted and participated in many group activities that created lifetime of friendships. Everyone was always welcome in our house. He loved food and entertaining people. My father was very humble and had great empathy for people. People enjoyed his warmth, his hospitality, and his sense of humor. As a person, he was totally non-judgmental. All his juniors, especially in the later years, it would come to a surprise to many that when he has worked as a consultant to many private concerns, all his juniors enjoyed the adda with him, with a senior colleague who was in his 70s. In fact, during when he was hospitalized later, we never had shortage of volunteers or all these young people who were still entertained by him even in hospital. My dad was very humble and had very simple needs. He did not beg for any awards or honors. Like I said before, this series would be a surprise for him, and I'm very grateful for that. He himself personally, he only liked one of his achievements. That was he came first in the order of merit for the first ever examination conducted by the first of the IITs, that is in Kharagpur. He was the first batch from IIT Kharagpur. So he came first in their examination. So he really enjoyed that record. Beyond that, he didn't even look for any awards. Though he had many distinguished firsts, which were mentioned just now. These lecture series also have given me and my family a wonderful glimpse into his professional life. I once again thank the director, Professor Shri Satish Chandra, the head, Dr. Rajiv Goel, all the members of the Bridge Division who feel like family to me, and it's lovely to see all of you again, and the IT team for organizing this. Thank you very much, all of you, and I'm sure you will enjoy your lecture. Thank you so much.
Thank you so much, ma'am, for these wonderful insights. Now I invite Professor Satish Chandra, Director CSIR CRRI, for his address, who has been a continuous source of inspiration and guidance to all of us in organizing this event. I request you, sir, to address the gathering with your encouraging words.
Thank you. Thank you, Dr. Naveed. First of all, I must say thanks to Sri V.N. Hegde ji, the CEO of Stoop Consultants, for accepting our request to grace this occasion and deliver this Dr. P. Raychaudhuri Memorial Lecture. It would have been really a great pleasure for all of us, Mr. Hegde, to have you in the institute in person today. But due to this current situation of pandemic, we are organizing this event virtually. But this in no way undermines the importance of this event. And as Dr. Rajiv Goel was telling you, that institute was set up in 1952. And other than bridge engineering structures, we have 6 more divisions who are working in different areas related to road sector. I'm just saying these lines because there are many participants from outside CRI, and that is the advantage of having online lecture like this, that you get participants from across the country. The 6 divisions other than BES, geotechnical engineering is one, which basically deals with the landslides, ground improvement, use of marginal materials in roads and embankments. Then we have 3 divisions of payments. One looking after exclusively for flexible payment, another for rigid payment, and third for payment evaluation. And the emphasis of these 3 divisions is to introduce new technologies, new methods of construction, new designs, and how to make minimum use of natural resources in road construction. So they are working on industrial waste, they are working on recycling of payments, they are working on advanced techniques of evaluation, payment management systems, asset management system, and many more areas. The next division is traffic engineering and safety. Their main focus is on traffic safety, of course, but providing the congestion solution to the cities. So in fact, CRI was the first institute in the country to introduce the concept of this comprehensive mobility plan for a city, and introduce this concept for a city like Delhi and Nagpur way back in, I think, 60s. Currently, we are working on the city of Ahmedabad, Noida, and Ranchi, and many more. Traffic planning environment division, that is the last division out of this list, and they are mainly concerned about the environment and planning of the transport system. So recently during this pandemic also, we organized some 6 webinars in different aspects of area related to road sector, and they were attended from engineers, from students, from professionals across the country. Now this lecture series, which was started 2 years back in 2018, and this was the first attempt in CRI to create some endowment fund for such activity. And it naturally took some time to materialize, to convince our finance officer and our administration that this kind of activity can go, because it has been the practice in all IITs and NITs. And I am happy that finally we could start it in 2018. And this is the 3rd lecture, which is being delivered now by our guest today, Shri V.N. Hegde. So I'll not take much time. I say again, thanks and welcome to CRI for delivering this lecture. Thank you very much. Jai.
Thank you.
Thank you so much. Thank you so much, sir. Now it is the time for which we all have been waiting for. Without taking much of time, I will quickly introduce our invited speaker, Mr. V.N. Hegde. Mr. V.N. Hegde is presently the CEO, Chief Executive Officer of Stoop Consultants at Mumbai, and former to that he was the Executive Director of Gammon for almost 32 years. He is a senior professional with a rich experience of over 3.5 decades in the construction sectors in the area of design management, technical management, site management, project management, and contract management of highways, bridges, engineering, energy structures like chimneys and cooling towers, environmental and marine and hydraulic structures. He is a recipient of around 9 national recognitions in addition to an international prize from various institutes like IRC, ICI, NDRF, IBC, and IABSC. He has more than 140 publications to his credit and is a member of various IRC and BIS committees. He is also a member of TG 1001 of Federation International du Britain, which is a special task group working on FIB Model Code 2020. Apart from being a technical board of ICI and academic board of SPCE, which is Sardar Patel College of Engineering, he is also a fellow of Indian National Academy of Engineering, FNAE. I thank you so much, sir, for accepting our invitation and gracing this event with your presence. I request you to kindly deliver your talk on the topic Lessons Learned from Bridge Failures. Over to you, sir.
Thank you very much. All of you can hear me?
Yes, yes, we can hear
Yeah,
you.
that's not a problem, right? And all on the screen that my presentation is there, right? Everybody is
Yes,
able
sir.
to see that.
Yes.
Yes, sir.
Okay, fine. Respected dignitaries on the virtual dais, Dr. Satish Chandra, Dr. Lakshmi Parameshwaran, Dr. Goyal, and others. I am very grateful to you for being invited to deliver a lecture on Dr. P. Raychaudhuri Memorial Lecture. Today I heard about his accomplishment. It is our accomplishment is nothing in front of him. I could say that, and it's really an honor. I consider it as a privilege to be a third speaker following Professor Tandon and Dr. Tarun Kant from IIT Mumbai. It looks like coincidentally that I've chosen a subject which is very sort of fond of Dr. Roy Chaudhary, Chaudhary. So it is mere a coincidence, in fact. But maybe the CSIR as well as CRRI, the doctors may be aware of his proximity towards repairs and rehabilitations as well as accidents. Now, all of us know that the civil engineering is one of the most noble profession. It is not no less a noble profession than doctors and lawyers as well as the scientists. They contribute to the growth by providing reach to the educations, health, transportation, creations of the job, as well as the tourism. I'm going to explain how they are going to contribute to the tourism. And they have created monuments which are changing the civilizations. And most of the times, whenever the people are traveling abroad for the tourism, it is some of the artifacts which are not to be missed by the tourists. Tourists are, as you can see here, the artifacts like Roman aqueduct on the right side of the slide, you can see it, as well as the Gateway Bridge in London. But the civil engineering work, especially the bridge construction work, is very manifestable in the sense whatever we do, they're out in the open and it can be seen. Unlike other professions like doctors can bury their mistakes in the grave, and lawyers as well as the judge can argue them out into the thin air, but civil engineer cannot blame the shortcomings to the predecessors and get away with like politicians. So it is there. Whatever his work, whether it's a good work or a bad work, it is totally manifestable and it's open there to be seen. In view of the lot of technological advancement which has been taking place all over the world in the materials science as well as the technology itself, bridge engineering also has to keep pace. While keeping pace with the bridge engineering, it is necessary to innovate, and some of the innovations and the practices which are going to be adopted may be not the time-tested solutions in the sense which were not done in the past, which has to be done first times. Unfortunately, the success in civil engineering is not a lesson learned, but the failure is. How? Just to give an example, I might have, in my 35 years of experience in last 3 decades, might have designed and constructed numerous number of structures, but that success, which has been structures which has been standing as a testimony of the successful design as well as the construction, cannot justify my engineering practices, while couple of mishaps which might have occurred in my career certainly tell me some of the practices which are wrong in my engineering practices. That is how the failure is a lesson as well as the success is not in the civil engineering. Coming to the bridge failures, till 2005, Wikipedia compiles there are a lot of rampant of failures all around the world, including the Western as well as the European countries. But there is evidence these bridge failures are being shifted into Asian countries. And there seems to be a relationship between the economic growth as well as the structural failures, similar to the relationship between the infrastructure development as well as the increase in GDP. all of us are going through this COVID period. If at all any country has to increase their GDP or the economic growth, if they have to accelerate, one way of doing it is the investment in the infrastructure. So to sustain the GDP to the extent possible, I expect our country also to be investing heavily in the infrastructure. And as such, you are already seeing in the offing many of the long, very long span bridges like Sahibganj bridges in the offing, Dubri Fulwari bridges in the offing. There are 5, 6 bridges like the Prayagraj as well as Bhagalpur bridge. So many bridges are offing, in the offing as a part of the infrastructure development. So I personally feel there is an urgent need to look into this bridge failures. As I was preparing the presentation for this Dr. Raychaudhuri Memorial Lecture, only the 2 days before there was an unfortunate accident, as could be seen on the right side. So are these accidents the act of God, as it was, put in one of the papers during the accident which took place for the Posta Bridge in Kolkata? Certainly they are not. Many of them are not. One non-vigilant but vital problem has not been recognized, has been underestimated or recklessly treated. That is the reason the accident could have taken place. Sometimes they are dictated by other objectives like cost, aesthetics, as well as the political pressures. And some of the times also the larger than life image, taking the engineering decision making to safeguard this image in a hurry to complete certain jobs, also the accident takes place. So among this, what is best for us? The best is way to generate a failure on your job is to disregard the lessons to be learned from someone else's failure. So it's always better for us to learn the lessons from the failures which has taken place. That too, if one can learn from someone's failure, that is very, very good for us. The failure takes place because of the human factors like negligence, incompetence, oversight, greed, disorganization, miscommunication, misuse, abuse, as well as the neglect. According to Motosek, as well as the Snyder, the ignorance, the carelessness, as well as the negligence accounts for 35% of the failure, while the insufficient knowledge accounts for the 25% failure. Whereas in the bridge engineering, it has been, that as per the record, 30 to 33% of the failures take place because of the floods, 15 to 16% of the failure takes place because of the scar, as well as the design, as well as the construction errors account for around almost 13 to 14% of the failures as per the records which we have gotten. Out of the natural, the man-made failures in construction, out of the natural human errors which take place are improper estimation of the loading, improper geotechnical assessment, improper planning, accidents and fire, collision and fatigues, choice of the contractor, extended duration of the construction, inappropriate methods of construction as well as the erection, inadequate foundations, defective workmanship, mechanical and electrical breakdown, inadequate site management, defective temporary works, inadequate permanent structure design, inappropriate construction process design. There are also natural calamities which causes the failures like wind and cyclone, earthquake and tsunami, floods and hurricane, avalanche and landsliding, extremes of temperature, inclement weather, excessive rainfall. Sometimes the structure itself, bridge itself is not accepted by the habitats. So why it is very difficult for us to, load test the, as well as by load testing, taking care of the failure in the civil engineering structure, especially the bridge structure, is because it's a size of the structure or also of the one of nature. It cannot be, it is not possible for us to conduct the pilot series of the simulated load testing like what we can do it in the car making. It is one of in nature. All the components of the civil engineering structures, especially the bridge structure, cannot be load tested before the construction itself. We cannot conduct the pilot series of the simulated tester. Whatever the load testing is available, it's always sort of a displacement control, and it is not load control. Displacement control in the sense when we do the pile load testing, we do the displacement, and the specimen is, the soil is flexible. And also when you are doing the load testing of the entire bridge, again, it is, it's a displacement oriented. It's not controlled by the load like, but in reality, the structure fails because of the abruptly, suddenly, and it's all in a way a brittle failure. You see that. The most of the failures, many of the failure to the tune of around 15%, as we have seen in the earlier slide, is because of the foundation failure. And there is, somebody has said, the wise man has said, there is no glory in design and construction of the foundation, but there is a glory in abundance. That is because the foundations are invisible, unlike the superstructure. Superstructure is given a lot of attention, and it's also it is given a lot of accolades. That is because of that, the people say that there is no glory in design and construction of the foundation, but there's a plenty of glory. But civil engineering foundations, especially the bridge foundations, nowadays involve five disciplines of the civil engineering, like geotechnical engineering, geological engineering, hydrological, structural, as well as the environmental. Environmental engineering has got added recently. So in case of the foundation, improper soil investigation, sequence of construction during execution, inappropriate score estimation and consequent conception of the foundation, artificial condition leading to disappearance of the foundation, erosion of soil due to the water below the temporary structure during construction. These are some of the factors which account for the foundation failures. Also, the conception of the foundation itself lead to the improper quality of the construction. Say, for example, conceiving the well foundation in a highly congested city areas may not be a right choice, because normally whenever the well foundation is done, there's always a possibility of the sand blowing taking place. And when the sand blowing takes place, the side by area is subjected to the subsidence, and the buildings as well as the road which is there can undergo the settlement, and the failure can take place. I've just put over here on a sand blowing slide over here. This you can see here, how the sand blowing can take place. This will just give an example. Sometimes it is slanted. All of you can see, right, Dr. Kaur? It can be seen, right?
Yes, sir, we can see it, sir. Moving.
So you can see that here, the continuous sand blowing is taking place, and the crane which is there has settled down, completely settled down, as you can see here. And similarly, the side by areas will undergo the subsidence. Because of the subsidence which is the settlement takes place, if there are structures around, those structures will come down. This is a slide, the continuous sand blowing which is taking place, and the people who are taking the video are talking about idhar palat sakta hai, udhar palat sakta hai, we can see. So this is the reason it is always better to avoid the well foundation in the congested cities. Yeah. This is what the sand blowing all about. So it's always better to. Also, there are sometimes artificial conditions are accounted where there are instances the well foundations have completely disappeared. And also the conception of the well foundations on the sloping rock has to be revisited. In important bridges, it may be good idea to conduct the geophysical studies before really conceiving the foundations. Otherwise, there's a possibility of the entire foundation getting redesigned and also the project completely getting delayed. There are instances where because of the sloping rock, well foundation could not be completed, could not be plugged, and the well foundation is abandoned and the entire project itself is abandoned. I'm just showing one of the bridges, or the railway bridges, wherein the well foundation was conceived on the sloping rock, especially for the foundation 17 and 18. It was a double D foundation of the 11 meter by 17 meter foundation. because the well foundation was conceived, and when the well foundation tries to reach the level of the sloping rock, it's not possible to plug it. This problem was envisaged earlier itself. The design has to be redone, and in the staining, the conduits were to be provided. In the conduits, the piling was proposed, and 12 number of piles, at one point, 10 number of piles were proposed in the staining, and the jet grouting has to be done all around. Once the well foundation is sunk almost up to the 1 meter above the ground level of the sloping rock, after having done the jet grouting, the plugging of the concrete, plugging of the well was done. After doing the plugging, 6 number of piles were done earlier before the plugging, and after the plugging, another 6 number of the piles were done through the already left the conduit in the staining, and the piles were anchored into the rock by 10 meter. These are some of the photographs, and also to make sure that the well is not slit, and because the jet grouting has to be done almost at around 40 to 50 meter depth of the foundation, and the quality of the jet grouts may not be that good. That factor was taken into consideration, and another 10 number of the piles were done all around the pile, all around the well, and this was also anchored into the ground, and these piles were integrated with the well cap, so the horizontal force which is inducing will not cause any problem to the well foundation. This bridge in Delhi is a well-known bridge, one of its kind in the world. In this bridge, there is a P23 foundation, which is there on the right side here. It's a very famous, internationally popular P23 foundation by this time. And in the forest area, this P22 onwards was lying down in the forest area. Because it was lying down in the forest area, there was not proper time or the opportunity given to do the geotechnical investigation during the tender stage. And after having secured the job, contractor had to do the geotechnical investigation. When the geotechnical investigation was done, it was all around the periphery of the well. And this was the P23 foundation is a very important foundation which had an uplift of around 6,100 ton in this direction. To neutralize the uplift, we had the pendulum bearing over here, which can take the tension up to 6,100 ton. And there were two well foundation of 17.5 meter was connected by a well cap of 4.5 meter. And then it was, the shaft was connected through the pendulum bearing to this backstay anchorages over here, by which the tension is transferred. And this being a very, very important foundation, the peripherally on the all around the well foundation, when the geotechnical investigation was done, it was observed almost to the tune of 9 meter, there was a variation within the well foundation in the sloping rock. And it was realized it's not possible to do the well foundation or possible to sink the well foundation without the tilt and shift. And it was not possible to plug the well foundation. In view of this, similar to that of the Jogi Gopa bridge, the 16 number of 1.2 meter dia piles were conceived. The entire foundation was to be redesigned, and this has to be through this conduits. The piles were driven, and the piles, for driving the piles, additionally the RCD rigs have to be imported, and the job which was to be completed in 4 years had taken 8 years because of this kind of conception of the well foundation. Perhaps it is ideal to conceive such foundations as a pile foundation whenever the sloping rock drastically is encountered like this. Also, there are false work failure because of the during the temporary structure trestles are subjected to the settlement during the construction. This unequal settlement of the column feet due to different flows and locally different subsoil conditions, and sometimes misalignment of the support due to the excessive soil compaction leading to the unscheduled horizontal force can also cause the failure. And there are instances like what happened in Hyderabad, the flyover, the soil beneath the temporary trestle being eroded, and the settlement of the trestle takes place, the settlement of the trestle leading to the collapse of the structure. And in this case, what exactly happened was, this was a precast segmental construction. the precast segmental construction, in the sense the precast were cast, segments were cast in the long way casting yard, brought into the location, put on top of the trestles, as you can see here, on top of the longitudinal girder. After this girders, the precast segments are put on top of it. This is pre-stressed, and once it becomes self-sustaining, these trestles have to be removed and the structure has to go on. The span of P16, P17, and P18 was going on. Actually, there was a water pipe being laid in the span of P21 and P22 and P23. And after having laid the water pipeline, and due to the imminent monsoon season, the contractor, the agency, which is not the contractor, this part of the work was to be done by some other agency, and that agency had to close the pipe. This backfilling had to be done. The water pipe was laid down, and the monsoon was approaching fast. The work was to be stopped at that particular point of time. The pipelines were kept open-ended on either side. On one side of the on the right hand side, the water was stagnating at the higher elevation, and the water which was stagnating the higher elevation could have seeped through this pipe and come up to this level. And one fateful day, on Sunday, it rained heavily for 3 to 4 hours, and the water stagnated on the right hand top side. And because of the gravity flow, water got into this pipeline, water started gushing in, and after having gushed in, it started soaking the backfilled soil over here. When the backfilled soil was soaked, this backfilled soil, after having become slush because the water which has gushed inside started seeping inside to the pipeline, as you can see here, which led to the settlement of the trestle, and the segments which were put on top of the trestle was not pre-stressed, and it had not become the self-sustained at that particular point. Unfortunately, this sort of accident took place. If there was a proper, so this is how it happened. This is one of the photograph you can see over here. This pipeline was done. This is a hard strata. The excavation was done, and 1 or 2 meters below the ground level, the pipelines were laid, and on either side, pipeline was left open, and the backfilling was done. The rainwater gushed in, and during the investigation stage, when the excavation was done and seen, this backfilled material had gone inside the pipe. As you can see here, when the backfilled material has gone inside the pipe after having become slush, naturally the settlement of the trestle taken place, and which was supporting this superstructure which collapsed. And score estimation, overestimation of the score in the Boulder data also has led to the prolongation of the projects in many of the projects. And earlier days, when for the Boulder, as far as the conglomerates data, the score depth calculation was to be done. The score depth calculation was done using the Lacey's equation, which was meant for the alluvial soil, alluvial soil. And you can see here, when using the Lacey's equation, these are supposed to be the silt factor or the silt used in calculation of the scour depth. If you use this boulder, which is there in the strata, geotechnical strata, and naturally the scour depth are going to be, very high, and it is not correct. But I think we have, perhaps found the solution for this. And because of this particular bridge had taken 20 years for the completion, and ultimately, after having done the model study, the founding depth was raised by almost 20 meter. Also, it's important for us to have the proper choice of the location. In the hilly terrain, the location of the bridge selection shall be devoid of the protruding unstable rock mass, causing landslides. Detailed geotechnical as well as the geological investigation, including the study of the seismic shear zones, also is necessary before doing the taking of the project. This is one of the bridge projects in Jammu area, and This job was to be discontinued because later during the investigation, it was found that there was a shear faults, active shear zones, and the alignment was found to be not suitable. The alignment has to be totally changed after having done completely the design, and design of the superstructure was completed, as well as the approach foundations were done, and the steel fabrication yard was set up for the fabrication of the superstructure for the approaches as well as this. So it is very, very important for us to geological as well as the geotechnical studies before taking up the alignment, about taking up the job and fixing up the alignment. There are also instances where the failure takes place because of the flooding and cyclone. We are seeing that almost 33% of the bridge failures take place because of this flooding and scene. It is because the country like in India, that the Brahmaputra as well as the Ganges, it is the rivers come from the Himalayan terrain. There's a possibility of the spatial variation up to even 15 to 20-meter variation in the river. That can take place because of the flash floods, and this variation can take place in the water levels within 24 hours, sometimes in few days, and the water velocity can go up to 8 meters per second within a certain time. So the factor leading to the failures of lack of hydrological data upon which to base estimates of the magnitude of the floods for the design purpose, ignorance of the hydraulics of flow in alluvial river, predict the occurrence of the impact and the accumulation of debris. I think perhaps we have to be trained in our hydrological study data. And some wise man has said that is why those who overlook the water under the bridge will find their bridges under the water. I think that's so aptly said. This failure doesn't take place because of the this kind of failure, that because of the ice movement doesn't take place in India. This I have not heard taking place. I just thought even due to the movement of the ice, snow, which is hardened snow, also the failure take place. It is an old Niagara Bridge which was constructed in 1898, and because of the ice which has been there at the springing point, because of the movement, the springing point collapsed, springing point failed, and the collapse had taken place. And also there are instances where the score calculation has been underestimated. Because of the underestimation of the score calculation, earlier I had shown the delay of the project because of the overestimation, even because of the underestimation of the, there are many instances where the bridges have failed. Many times, coming to the superstructure now, many times during the executions, the designs are changed. These changes in the designs are seemingly unimportant. Sometimes the seemingly unimportant changes cause the failures. And also sometimes possibilities of the failures were never visualized, change sequence were not thoroughly investigated, or that in some way rashness was predominant during the design or construction to meet the deadline. Most of the time, when the job is done in hurry to meet certain deadlines, the changes in the designs are done, and when the design are changed, which may be looking unimportant, that will lead to, that has led to the failure. So it is necessary for us to do the thorough investigation when the design is changed during the execution. There are also scale effects. We engineers have got a quest for, designing a very tall, very slim, very wide, and very long and larger structures. We want to create records. And if there is a chimney of 275 meter, we want to design the chimney of 276 meter. Unfortunately, there is no law to restrict the tallness, length, and largeness, and find stretch solution under the constraint situation. Sometimes the secondary effects for the small structures which was not governing the design and which is neglected, which can be neglected during the design. When the scale effects are there, when you go for the taller and longer structure, the secondary effects may become the primary effects and causing the failures, which is not time tested, of course. So these secondary effects has to be considered. Whenever we are doing the time untested structure, it's very necessary for us to conduct that. If there is a classical failure of, Koror Babuldev Bridge collapse, which I'm going to take up in the next slide. And that is because, the secondary effects estimations were not done properly. There are a lot of excessive deflection in cantilever bridges, and some of the bridges have been repaired by the external pre-stressing, and some of the bridges have been replaced these days. And this the state of the art technology for the balanced cantilever or the free cantilever construction available in 60s to 80s were used, and the creep and shrinkage models were used. Because of that, at the mid-span, where the articulation is there, the excessive deflections have taken place. But this phenomena is not confined to Indian subcontinent. It has been reported all over the world. More than 100 to 150 bridges have been excessively deflected, which were constructed using the state-of-the-art technology which was available at that point of time. Karor Babaldev Bridge, as I said, in Palau was considered to be a spectacular, though the collapse can be called spectacular, but in the literature it has been mentioned as a spectacular collapse, which gave rise to the new models of the creep and shrinkage, which has been adopted all over the world now. This bridge was constructed in 1996, and when it was constructed again, it is a scale effect in the sense it was the world record-breaking span of 241 meter. Within 18 years, excessive deflection of 1.61 meter took place. There was an excessive pre-stressing loss of 49%. Remedial external pre-stressing was adopted. After having repaired with the external pre-stressing, within 3 months, the bridge collapsed, and it was called a spectacular collapse, as I explained earlier. In the 18-year mid-span computer deflection, as a percentage of the measured deflection were, as per the CEB FIB model code at that particular point of time, 34%. ACI code, it was around 31%. RELIM B3, it was 57%. And similarly, the pre-stressing losses were 48%, 44%, 80%. RELIM model was found to be closer to the reality in terms of the long-term deflections as well as the pre-stressing losses. But this collapse made all our scientists to study this creep and shrinkage in detail, and all over the world, creep and shrinkage models was changed after this spectacular collapse, including in our IRC 112. And many of the bridges is being constructed these days using this creep and shrinkage model. Over the period, we'll have to find out as to what will be the result of this creep long-term deflection on the cantilever bridges. It is not time tested. There are also many failures that change the perception of the design. Because of these designs, because of the collapses which took place, had to change the design rules. One of them is all of us know it's a galloping jerty, that a Tacoma bridge failure in 1940 because of the vibration due to the aeroelastic fluttering. And in case of ferry bridge failure, though it's a cooling tower failure, it's known as a ferry bridge failure. That's what I thought. I'll give this example. There were 6 cooling towers. According to the eyewitnesses' account, all the 6 cooling towers were dancing before 3 of the cooling towers, like a belly dancer, because these 3 of the cooling towers collapsed later, and that is why it's called belly dancer. It is interesting to note that these 2 collapses perhaps resulted in the revision of the building codes all over the world to include the wind tunnel test for complicated configuration as well as the arrangements. And there are also, the bridge failures because of the overloading, taking the consignment more than 400 and 600 ton without checking the old bridges whether it can carry this one. The classical case is a bridge failure in Himachal Pradesh, where the truck which was carrying the apples was stopped during the daytime, but during the night time, the driver tried to take over this truck over the bridge, that the bridge collapsed. Similarly to that of bridge which collapsed in Gujarat, which was carrying the boiler weighing around 400 to 600 ton, and the next day, while it was being carried over, it fell down into the water. There are also bridges which failed during the construction due to the over design of the scaffolding. This is one of the aqueducts which I was involved in the design of the permanent structure, and it collapsed because perhaps we had a lot of staging material. We thought it's on a conservative side. We provided the scaffolding structure. Because of the hurricane, this scaffolding became almost opaque to the wind forces, and during the cyclone, this scaffolding failed. So sometimes because of the over design, also the failure can take place. Also, there are many accidents during the construction due to the unscheduled overload, underestimation of the wind load, defects in design, structural analysis and construction, unknown or unrecognized phenomena sometimes, especially when you are addressing the taller, slimmer, and which are not the time-tested structures. It happens. Unrecognized risk, unrecognized or disregarded instability. It happens many times. Irresponsibility during construction, material defects including concrete strength, failure of machine or one of its parts. All the above causes in some or the other way connected to pressure to complete the job hastily, either due to the ignorance or indifference. So it is necessary for us to not to come under the pressure, in my opinion, so that the investigation for those things take place. Here is one of the cases which I have highlighted here. As you can see here, this is a second Hooghly Bridge during the construction. It was a prefabricated segment and pylon construction. Pylons were prefabricated, brought to the location, had an arrangement of the climbing crane. As you can see here, this climbing crane was mounting a winch. Winch could have slewed on the left side or the right side. Whenever the segment has to be lifted on the left side, slewing the wing to the left side, the segment was to be erected, and once it is put on top of already erected segment, here perhaps the riveting was done, and the operator, maybe because of the ignorance, he or under the pressure, whatever it is, he slewed, he operated both the winches together, which induced a tension on the self-climbing crane over here. This tension broke this particular crane. So it can happen because of the operations which is indifferent and indifference. During the construction of the elevated corridor, also the many failures had taken place, and some of the failures have taken place during the concreting. The scaffolding failure had taken place during the erection. Launching girders have taken place. These are the two failures in the Chennai. Also in Mumbai, like during the concreting, scaffolding, as well as the launching girder failure had taken place. There are also spurt of failures in Delhi too. In one of the elevated corridor construction in Delhi, the span, which was the prior span, was already put into the position, and the pre-stressing was done, and the launching girder was to be auto-launched to the next position. When the launching girder was completely auto-launched to the next position, as you can see here, that the span number 6768 was put into the position, and at that particular point of time, the structure, this is the position where the launch, this span is already put into the position. Pre-stressing of this span is done. This has become the self-sustaining. The launching girder which was there on top of this, is auto-launched into the next position for the erection of the span under this, as you can show over here. And at this point of time, and this structure, which had a crack over here in the pier cap, which was the crack which had appeared perhaps 3 months back, was investigated thoroughly, and for whatever the reason, it was felt as an additional factor of safety by provision of the struts, by the provision of the struts, which is seemingly an unimportant insertion. Basically, the further erection can go on. And after having deliberated for 3 to 3.5 months, this decision was taken. And when the 5 of the segments in this particular launch span was erected, the unfortunate the failure had taken place. Also during the Commonwealth Games, there was a couple of more accidents which took place at the time of one of the foot over bridge, as you can see here, was failed. It was said that it is because of the wrong orientation of the gusset plates. But however, the investigation committee said that the methodology of the construction adopted to complete the job in a hurry for a Commonwealth Games were the responsible for this failure. There are also the other failures at this at that junction of around 2006 and 2007. The bridge which collapsed in Kota, Rajasthan, was a very bizarre and a very dramatic failure among all those sort of failures. This particular bridge, which has been completed and standing now, is the first axial suspension cable stay. So actually suspended cable stay bridge in India, which had a 350-meter span over the river Chenab, and it was a free cantilever construction. The pylon was to be constructed. On one side, there is a back span which acts as a counterweighting for the free cantilever construction, which has to be go on that. When the free cantilever construction was going on, the bridge collapsed very dramatically, as you can see here. The bridge which was there, according to the eyewitness, was standing on the other side of the bridge, and also some of the eyewitnesses were standing near the bridge. The farm traveler, which is there here, started tilting on another side. The farm traveler as well as the pylon together started rotating in this direction. And after having the farm traveler along with this cantilever span had hit the ground, the entire back span was catapulted almost 100 meters away into the river. And in the collapsed condition, the study of the debris indicator, as you can see here, this is a cantilever span which is there here, which had rotated like this as well as hit the ground, and this was lying down upside down over here. This is the pylon which was there, which was inside the river, as you can see over here. And believe it, this is the back span which is there here. The back span has toppled on top of this upside down. That was the impact of the collapse which had taken place. And it was a very bizarre and abrupt failure. These are some of the use of the debris, as you can see here. This is the cantilever box girder upside down here. This is a span P4, P3 box girder. And this is the back span. In fact, that the pylon pier was at the center line of the pylon pier was over here. And behind this, which was back span, was over here. The back span was thrown into the river almost 100 meters upside down. As you can see here, another view of the debris over here, that after the debris mapping was done. During the construction, as per the original design, the pylon was to be constructed 40 meters and the free cantilever construction was to go on, and the back span was to be constructed like this. In the revised design, as approved, of course, the pylon was constructed, revised design. After the revised design, the construction was already done. In the revised design, in deviation to that of the original design, the pylon was constructed 80 meters tall and the free cantilever construction was going on. Of course, the revised design was approved over here. This is my interpretation as far as the collapse is concerned. It's a personal interpretation of this collapse. What exactly happened? I think we'll have to learn a lot of lesson over here. In fact, what exactly happened? It is not very uncommon that the farm traveler failure take place. According to the eyewitness, the farm traveler started going down. Once the farm traveler went down, there was also the falling of debris in the back span, as you can see over here, according to the eyewitness. This back span has been cast into two in stages. This is the first stage concreting, and this is the second stage concreting. And there is an interface shear which comes interface between the new concrete as well as the old concrete. When you look at the interface shear, we can think about this, the back span. When the impact, there's a possibility of this particular the segment which is cast in situ, which was weighing around 100 ton, 120 ton, including the weight of the farm traveler, may fall down. There could be a free fall of this segment. Also, may not be a free fall. One of the bolts of the farm traveler, which is in the transfer direction, might have given away, and the other entire load might have started coming down. And since another bolt is not detached, it is just attached to this structure. It is different from that of the free vibration, free fall of the concrete segment. It is like throwing 100-ton load from this height to this. That impact, that is a forced vibration. This vibration effect, if it is 100-ton is thrown 1 meter from top to this, that impact is 2 to 3 times the impact of free fall of this segment. If this dynamics has been understood, there will be a shear force which has been induced in this back span, and this shear force, when you check for the interface shear, and there is a possibility that the interface shear failure could have taken place over here. This is only my personal interpretation as far as this is concerned. This sort of possibilities also will have to evaluate during the designs as well as design, in my opinion. All these things are the failures due to the inability to visualize the accident scenario, as you can see here. Some of the factors could be improper selection of the designers and absence of the third-party checking, inadequate time and resource allocation for completion of the design, changes in the design concept and the change of designers itself, absence of robustness in the design, complex structures and analysis rather than simplicity in designing, modeling very compactly. I think I just lost this file. I'll just come to you. Yeah, this is where we are. Extrapolation in design assumption, neglecting the scale effects, reliance on computer and software for analysis, design and detailing without experience. We have to rely on computers as well as the software, but that has to be done with the experience. What input is there, what comes out, we'll have to be very careful about it. And the unconstructable design also sometimes responsible for the failures, bridge failures. There are also instances, as reported in the media, that the bridge which are designed, which are in curvature, are designed as a straight bridge, and even the bearing configuration has been laid down as if it is to the straight bridge instead of being in a curvature. After the superstructure is pre-stressed, when it became self-sustaining, the overtoppling has taken place. And also there are bridges collapses in Calcutta. It's a Ulta Danga bridge. It was said in the media as well as the report that this bridge collapsed because of the wrong orientation of the wrong placement of the bearing itself, where tension bearing has to be provided. It was not provided, and during the traffic, when the overloaded truck was going on top of this bridge, it collapsed. That's a classical case of Costa, which I showed you earlier, whether it's an act of God. And it was said in the beginning, certainly here we can see that it's not an act of God. It is, in my opinion, completely buckled, but also there are reports that because of the change in the improper sequence of the construction, also this bridge collapse, this flyover collapse at Calcutta is taking place. So the question here belongs to the category of accidents caused by an oversight arising out of inexperience and by neglecting to perform some basic stability calculations. I think that's what has happened. I think this is a lesson which we learn from these failures. And also when we travel in, many times I used to travel in Delhi from airport to the city, you can see a lot of piers which have been bulkier pier, as you can see on the right side, which is a jacketed pier compared to that these are piers. Especially in elevated corridors like metro, it has to be meandered through the very highly congested area. There are instances where the pier caps have to be conceived as a cantilever or a bracket like this. After, it is very ironical, like this, so many piers as well as the pier caps have to be jacketed like this after one mishap has taken place. In my opinion, it is because of the computer cut and paste. Earlier, one detailing of the pier as well as the pier cap was done, and it has been repeated by so many other designers later. And it seems to be an error of cut and paste where the detailing is already done, where the mistake of detailing was involved, and the same concept was followed by so many various designers. That is the reason later it has to be corrected. As you can see here, this is the pier. This is the pier cap, which can be also designed as this one. There is a possibility this pier as well as the pier cap has been designed by the different engineer independently. If you really look at it, if a pier is designed by one engineer and he has done the design of the pier properly and he has provided the necessary development length over here. Another designer might have done the pier cap. According to him, he has also done the design of the pier cap properly. But there is an area where both commonality is to be there, where the moment transfer has to be taken place. For the transfer of the moment transfer mechanism, proper detailing has to be done. Since these two pier cap as well as the piers are done independently, it's not holistically looked upon. Perhaps this kind of failure has taken place. In addition to what I said, the repetition of the computer cut and paste which has been adopted. Later, after the jacketing which I showed you for the various jobs, various piers as well as the pier cap, a scheme was developed for the jacketing, and the jacketing scheme was adopted, and the pier has been jacketed like this using the again the interface shear has to be worked out over here, and to make sure this there is a continuity of the moment transfer mechanism over here. The pre-stressing was done, or the PT bars, using the PT bars over here in the rehabilitation scheme. Another issue which leads to the failure is the lack of the robustness. The first definition of the robustness is not there in any book, but it is my definition. I define the robustness in the design is the ability to visualize permutation and combination of the accident scenario and catering for the same. If a person, if a designer as well as the constructor has the ability to visualize the permutation and combination of the accident scenario and caters for the same, many of the failures can be avoided. I call it as a robustness. It's a question here of an unwillingness to consider unscheduled and unlikely actions which cannot be completely ruled out, or of keeping the damaging effects of the incalculable action to a tolerable limit at a reasonable cost. It is also could be making sure sufficient residual load path is available one major load path phase. That is what it is. I'll just give an example. Take the case of a cable stay bridge, actually suspended cable stay bridge, which has got a spherical bearing on the pylon. It's a pylon integrated with the deck over here. This is supported on a spherical bearing which is free, and there is always a possibility of, as I explained, the form traveler failure. Also, during such construction, this pylon is attacked with the crane, the tower crane, and there is the tower crane as well as the pylon acts in tandem. There is a possibility of the unscheduled force which is coming on the bearings, which is free over here. These free bearings during the construction has to be frozen for the translation as well as the rotation for its stability. This unscheduled force has to be visualized and it has to be taken care of. That is what the robustness I called. So the possibility of failure of rotational and translation stress provided due to unexpected loads in this case, the mechanical failure of form traveler during concreting and consequence on stability has to be kept in mind, and that is how it has to be addressed. There are also risks of extrapolation. It's again, I call it as a scale effect. If you really look at it, this is a classical case of Rupnarayan Bridge, which has been well reported in one of the IRC paper by Sitaraman. as you can see here, this particular bridge was to this had a girder of around 48 meter, and this 48-meter girder was to be erected using the overhead launching auto launching girder. As you can see here, this auto launching girder was a aluminum basically truss, and when the first girder was erected, the collapse took place, and the design was checked once again. That time it was said that it's because of the error in the launching girder when the first girder took place. The design was checked, design was found all right. Again, this girder was strengthened, and again the second girder was being erected. During that erection, again the collapse took place. It happened 3 times, and then the proper in-depth analysis of the structure was done. You know what happened really? The secondary effects, which are not so dominant because of the, say for example, 25 to 30 meter of the girder, the secondary effects because of the imperfection, casting imperfection, which will cause the lateral stability, can be neglected. And there are some rules given in the codes that what should be the width to top flange width to the depth ratio that is meant for the RCC girder as well as the steel girders basically. But in case of the long pre-stressed concrete girders, in addition to this, the secondary effects are also there because of the pre-stressing dimension. During the pre-stressing, normally the property of the girder is always worked out vertically. The actual x-axis is perpendicular to this the vertical direction over here. The property has been worked out. The tension because of the pre-stressing has been found out here. And there could be an imperfection which is caused while doing the casting because of the pre-stressing is pre-stressing cables are slightly not at the center. It has come out, or there could be a bulging in the pre-stressing the casting of the girder itself. So these secondary effects induces the moments in the transverse directions as well as the longitudinal direction. For any reason during the transportation as well as the erection, this girder, instead of being vertical, if it is coming slanted to certain degree, the property of the girder itself will change, and the stress at the top will be totally different. And if you add in addition to that, the moments due to the imperfection, it may enhance. This is one of the reasons this girder 3 times failed. The secondary effects, these are all the secondary effects which was dormant so far. When we go on increasing the sizes of the structure, in the sense when they go on increasing the spans of the structure, especially to the untime tested levels, it's a possibility that secondary effects start dawning the design. That's what exactly happened. So in each case of extrapolation, one can identify a situation where in early example of the structural form, a certain factor was of secondary importance with regard to the stability or strength. With increasing scale, however, this factor became the primary importance and led to the failure. In case of the cantilever construction, there are, especially the steel cantilever construction, there are failure of compression members, failure of support trestle under cantilever, failure of tension member, failure of bearing crossbeam, failure of temporary pylon, failure of lower flange in compression, failure due to not following design procedure, which I explained, failure due to forced correction of the bridge form during the execution, failure due to false configuration of web stiffness. That has been the case in one of the CWG footpath foot flyover, which was explained. There are some of the example of the compression member as well as the tension member failures during the cantilever construction, as you can see here. In one of the cases, normally this steel bridges are erected by the cantilever construction or by the push launching method, and either one of the methods have been used. Normally during the cantilever construction, during the serviceability, see in cantilever construction, some of the members of the trusses, which during the service condition are in tension, becomes compression during the construction stage, and during the the vice versa too, it can happen. Normally, the bottom chord axial members, longitudinal members, always under the tension during the service condition, but during the construction, it can become it can become compression members too. In this particular case, there could be the cases where to hurry up the job, to hasten the completion of the job, the longitudinal members are extended further without putting the horizontal members. When you don't put the horizontal member at the bottom chord to break the slenderness ratio, to bring the slenderness ratio into the picture during the construction stage, this is under the actual compression and it can buckle. And due to this buckling, there are many failures have occur during the cantilever construction of the steel truss bridges. There are also many failures because of the external, without the external actions. That is basically because of the wrong, improper maintenance. The maintenance of the bridges are very, very important, and there are a lot of efforts are made for bringing out the methodology for maintaining the bridge maintenance by our government authorities, and that has to be implemented properly. Not only in India, even if you take the case of the Morandi Bridge, which was Genova in Italy, which has taken place a couple of years back. It was said that it was because of the poor maintenance and also improper robustness in the form of alternative load path. Morandi was one of the greatest bridge engineer. It is one of the variation of the cable stay bridge. The cables were basically encased in the concrete beam over here, and it was an ordinary piston cables, and it was observed sometimes back to the prior of the collapse, the inspection was done, and there was warnings of the cables corroding, and that warnings was not heeded to because of the bridge collapse. Similar to that of the Mondavi Bridge, it was a classical bridge failure after 17 years of the construction. It was said in the reports, investigation report, that the top cables, which was anchored, pre-stressing cables, were in the deck that had corroded because of the seepage of the water into that for a long time, and the failure had taken place. And there are other bridge failures which has served its purpose of serving more than 100 years, and the bridge collapses has taken place. And those bridges also could have salvaged, but for the maintenance. In conclusions, I would like to say that in case of accidents as casualties and related legalities are involved, the real and primary causes are not presented by those who have really experienced. As such, invaluable experience as a learning tool is wasted quite often. That is the reason I've taken up this presentation today. I've dared to take up this presentation today, though some of the failures are, but I have made sure that all this information I'm giving, it is in the public media, it is in the print. So from those information only I'm giving. Case studies of structural failures helps in understanding of our present state of technology and its limitation. Much improvement of our design concepts in terms of robustness, extrapolation, and durability has been possible from the study of failures. These provide an invaluable information about this design limitation. What is design after all? Design as well as the construction for that matter is nothing but anticipation of the failures and to account for it, to cater for that. That is all the design is about, whether it's a serviceability, whether it's for the strength, whatever it is, we'll have to anticipate the failure and make sure that the failure doesn't take place. That is the design is all about. In conclusion, I would like to say there could be little doubt. In many ways, the story of structural failures is the story of the lessons learned. By documenting it, we do great service to our posterity in improving safe and sustainable engineering practices. Thank you very much. I'm ready for the questions and answer session.
Thank you so much, sir, for enlightening us with these case studies related to bridge failures I'm sure they have highlighted the importance of safety measures to be taken care during the construction.
Hello?
Maintenance, importance of maintenance of existing bridges, sequence of construction to be followed during the construction, and also the importance of design and detailing to avoid such failures. Thank you so much, sir, for sharing for sharing this important information. Now, I request if anybody is having questions, we can have some questions. Dr. Goel?
Yes, yes, madam.
Yes, sir.
Yes, sir. Very good presentation, very exhaustive presentation. We learned a lot from you.
Thank you very much.
Thank you, sir. Sir, in my view, it will be better if the during construction, whoever has done the bridge, they also inspect during the construction. Bridge of the designer should be there during construction, so that if there is any change correction it to done, that can be done inside itself. What do you think, sir?
Yeah, absolutely. See, during the construction, what I was trying to highlight is if any changes have to be made, it has to be thoroughly investigated. Sometimes what happens is the changes are made thinking that it is an unimportant, it is a very small changes we are making. It will not affect the structure. And also sometimes the forms are forced to the corrections during the construction that has to be properly discussed with the designer as well as the approving authority before implementing any changes.
Yes, and one more thing, we should embed some instruments during the construction for the long-term assessment.
Especially, absolutely, not only from the long-term perspective. See, the construction, like the cantilever construction, cable stay bridge construction, extra bridge construction, it's all during the construction also. Perhaps I think we'll have to think of implementing some instrumentations, just to see what are the deformation taking place during the construction here and there. I think it's a good idea. And there are instances where the instrumentation has been done during the construction too, not only for monitoring the health of the structure after the completion of the job.
Hello, good afternoon, sir.
Good afternoon.
This is SS Gherwar.
Yeah, Gherwar.
First of all, my hearty compliments to you for an excellent lecture. I think best suited for this series.
Thank you very much.
One doubt regarding this your presentation, and one experience I would like to share with you. That two case studies, that signature bridge PR23 and this failure of this Shatrunjit river bridge, Gujarat failure. So two of the bridges CSIR, CRI has also been closely associated with. So
very good.
I wanted to share with you regarding this Gujarat bridge failure. Rightly said that overloading is one of the phenomena, but my feeling is that probably the condition assessment of the bridge over which the overload vehicle is passing, that is also one of the prerequisite requirement, and probably in this particular bridge that aspect was not given due consideration, since we are all closely involved with that. So that is my preliminary you can say observation. One slide which you showed, and I would like to know from you. You mentioned one of the probable reasons for failure is the extended duration of construction. Can you please elaborate, sir? Extended duration of construction.
See, sometimes what happens is, you see, for whatever the reason, say for example, pre-stressed concrete girder is standing over there, and for some reason the pre-stressed concrete girder, which was to be pre-stressed, and also after some time the grouting has to be done immediately. For some reasons, that grouting has not taken place, it's standing for a long time, there is a possibility of failure taking place. You know, see, you imagine a situation where a pre-stressed concrete girder is standing and the grouting of the cables is not done properly. You know, that could be the one of the reasons. Now, in case of the cantilever construction as well as the pre-stressed concrete continuous bridge construction, The creep and shrinkage also is a very, very important factor. Say, for example, while working out the creep and shrinkage forces on the losses on the structure, we assume certain number of days after which the pre-stressing takes place, right? So we assume that according to the calculations which you have carried out, if the construction doesn't take place, the real phenomena which really happens is different. That is because of the delay in construction. The creep which would take place, creep losses which take place because of the delay in construction is different from that of what you have calculated, what you on the basis of the time cycle which you assumed. Sometimes it happens. Extended period of construction itself is a failure, in my opinion. If the project has to be completed in 44 months, if the project is not completed in 44 months, if it takes, say, for example, instead of 4 years, it takes 8 years because of the wrong design concept. The concept of the design, conceptualization of the design itself is wrong. It's not right. If it takes 20 years, say, for example, one of the cases I gave, it was the wrong overestimation of the scour depth, right? Overestimation of the scour depth has delayed the project for 20 years, which was to be completed in 3 years. That itself is a failure, isn't it? So I am relating the extended period of construction as a failure because of that. There are so many reasons which we can give for that.
Well said.
Dr. Naveed, please.
Okay. Thank you so much, sir. Now I request the CCN team to help us to felicitate Shri V.N. Hegreji with a virtual memento as a token of gratitude on the behalf of CSIR CRRI.
Thank you very much.
Thank you, Mr. Mariappan, Mr. Vivek Dubeji, and the CCN team who came up with this wonderful idea of virtual memento and bouquet, which I believe is a apt substitute for the real memento, which has been already shipped, and we hope will, Mr. Hegreji, you will receive it soon.
Thank you very much.
Now,
Thank you.
my pleasure, sir. Now we are moving toward the end of this event. So I would like to invite the senior most member of our team, Dr. Lakshmi Parmeshwaram, to give the vote of thanks. She has, with her immense knowledge and experience, guided us as a strong pillar to organize this wonderful event.
In
I
fact,
request you, ma'am, to deliver.
Yeah.
Yes,
In fact, I want to share. It is Dr. Lakshmi Parameshwaran's idea to talk about this bridge failures. She suggested this topic. Thank you.
Great.
Thank you, Dr. Naveed. Respected Professor Satish Chandra, Chief Guest of the Day, and invited speaker, Mr. Venkatramana Hegde, and Ms. Debjani Raychaudhuri, Dr. Rajiv Goel, and all eminent participants whom we are not able to see you. Indeed, you all agree with me that we had a wonderful lecture full of case studies about the bridge failures. That is how it happens. Though we take care of them during the design, still the failures happen. And Mr. Hegde has a wonderful collection of case studies to present the various causes, starting from how the bridge fails because of the geotechnical problem, or if it is due to the change in the design during the construction, or it is the secondary effects, or it is the durability issues. So it's an eye-opener for all of us to learn from these failures and practice good best practice can be adopted in our design life, so that like the structures are safe. Thank you very much, sir, for accepting our invitation and delivering this lecture. And it is an honor for me to extend the vote of thanks, because we have been working closely in various committees for almost 2 decades. So it is a pleasure for me also, sir.
It's my privilege.
And on this occasion, sir, we have a special message from Dr. R.K. Bhandari, who is Honorable Research Member, Research Council Member of CSIR CRRI. So I am happy to read this for all this on his behalf. On this day, while paying my most respectful homage to the memory of my friend, late Dr. Raychaudhuri, I send my best regards and good wishes to score of his colleagues and admirers. Please convey my gratitude and sincere greetings to Mrs. Raychaudhuri and members of her family. And I thank Dr. Bhandari for his wishes to all of us and to the family members of Dr. Raychaudhuri. And I would like to extend my gratitude to Mrs. Raychaudhuri and Dr. Raychaudhuri's family members, his daughters, for trying to support CRRI for this event and also celebrate his research journey with this knowledge dissemination event. I think this is the best possible way how we can pay our respect and homage to Dr. Raychaudhuri. So in this event, I want to share an latest information. Actually, I found one paper of Dr. Raychaudhuri, which was written in 1973 and published in Indian Road Congress Journal. And the topic is design of retaining wall with relieving shelves. And this paper is available in the TRID database. And probably this was an innovative idea at that time and may not be a fully matured idea at that time, I would say. But I found that recently many of the Russian engineers and engineers from abroad, they have done continuous work on this topic, and also they have published many papers. And I found that some of these retaining walls are being built in India as well. And I found all these papers are having a reference of this paper of 1973. And what made me happy is that at that time there was no Google, no internet. So whatever we do, how it is important to do the documentation, probably that is what we have to learn from him. So even if we are not there, but somebody else will be using it. So that is a, I think, pride moment for CRRI also to share this, to have this success story of Dr. Raychaudhuri still continuing even after so many years. And Dr. Raychaudhuri, he pioneered research on well foundation, head stiffening of slab bridges due to integral curves, developed load testing and elastomeric bearing. And I'm sure that many of these aspects Mr. Hegde also covered in his lecture. I'm very, very happy for that. And I want to extend my thanks to Professor Satish Chandra for continuously encouraging us and motivating us to organize this particular event. And this would not have been possible without the help of our IT team and also each and every member of CRRI family, as well as the participants who are there. I am sure they would have enjoyed this. And I'm extending thanks to them for connecting with CRRI with this event. And I hope that they will continue to be with CRRI in all future events. Thank you very much, sir.
Thank you.
Thank you, ma'am. I think Mrs. Devjani, you want to add something? You can please.
I'll really like to thank Sri Hegde. His topic was very good, and even his presentation was excellent. And we were even, I come from an architecture background, but I was riveted throughout your thing. And though I'm working in the metro field now, but it was really useful, and anybody could follow it. So thank you, sir, for that. It was very well presented. And thank you, Dr. Lakshmi, for that priceless piece. Just new story which I heard. So this whole thing, through these, I discover the professional life of my father. And as a family, we are all very grateful to all of you for having this lecture series. Thank you, Professor Satish Chandra, Dr. Goyalji, Mr. Garwar, and all of you. Thank you so much. And it was, we really like this to continue.
Thank you, ma'am. Thank you. In the end, sir, you want to say something, Mr. Hegde, sir?
Yeah, I would like to particularly thank Devjani for inviting me and for this particular presentation. In fact, it's a privilege for me to learn about Dr. Raychaudhuri so much. Though I knew him, but I didn't know about his accomplishment as well as the achievement you have really put. He would have deserved much more accolades as well as the recognition, rather than just being recognized for being first in IIT Kharagpur examination. He deserves much more, and I'm very grateful to CRRI as well as to architect Devjani. I know that. Thank you very much.
Thank you, sir. Thank you. Now, in the end, I would like to thank all the participants, CSIR, CRRI members for helping us making this event a success. I hope this lecture has ignited a spark that will lead to further discussion and deliberations on the topic, and thus helping to achieve the original motive of this lecture series. Looking forward to many more such lectures in the years to come. Thank you so much, all.
Thank you.
Thank you very much.
Thank
you. Thank you. Namaste.
Namaste. Thank you.
Thank you, Devjani. I couldn't talk to you that day.